Hello, my name is Sahar Mavali and I'm presenting Time Turner, a Bichronous learning environment to support positive in-class multitasking of online learners. Let me first introduce you to Dan. Dan is a university student and he cares a lot about his education and his courses, but on top of that he has other social, emotional, and professional goals in his life. In order to get everything done, Dan multitasks in his classes because he feels like it helps him save a lot of time and be more productive. On the other hand, research shows that in-class multitasking can reduce Dan's learning outcomes and lower his grades. Studies also show that there are a lot of university students who are aware of the negative outcomes of in-class multitasking. Considering the substantial amount of in-class multitasking that happens in in-person classes, and even more than that in online classes, makes us think that maybe university students are actually benefiting from doing other things in the class overall, and the benefits of their in-class multitasking is more than its detriments for their learning. If that's the case, we should try to design to improve this trade-off by reducing the detriments of in-class multitasking. We define our first research question as what are university students' motivations, perceptions, and challenges in in-class multitasking in online synchronous classes. After learning that, we want to come up with design elements that can mitigate the consequences of in-class multitasking for learning while maintaining its potential benefits. To answer our first research question, we ran a formative study and asked 10 students to keep multitasking diaries in their online classes, and then we followed up with semi-structured interviews. Even though our participants found in-class multitasking to be helpful for their productivity, they found it challenging because of its consequences for their learning. We structured these consequences into two main groups to help us structure our design better. The first group is cognitive consequences, and the second one is metacognitive consequences for learning. Based on our overall findings in our formative study, we aim to support in-class multitasking in online synchronous classes and not eliminate it. Based on our cognitive consequences, we designed Time Turner. The main concept behind Time Turner is that it's a Bichronous learning environment, meaning that it's a combination of synchronous and asynchronous learning. This way, it helps students recover the content that they miss right away when they come back from doing another task in the class. Let me show you how that works. In the live mode, there's only one header moving on the progress bar. The student leaves the class to do another task like work on an assignment or answer an email. When they come back to the class, they will see that there's a gap on the progress bar showing what they missed. They can click on the beginning of the gap to start watching the content they missed in the recorded mode with a faster playback speed. In the recorded mode, they can skip back, they can pause the lecture, and as you can see, the live header keeps moving forward. They can skip ahead, and they can change the playback speed. The text over the arrow between the two headers shows how long it will take them to catch up to the live class. In the recorded mode, there's a picture-in-picture view of the live class. The student can click on this view to jump back to the live class quickly if they need to. When we allow students to watch the content asynchronously and choose the playback speed, they might ask, well, how fast should I watch the lecture in order to be able to catch up before the end of the class or before a quiz that is 10 minutes before the end of the class? In order to help with that, Time Turner allows users to set target times. If a student has a quiz in the middle of the lecture and they know the time, they can set a target time, and Time Turner will give them feedback on how fast they should be watching in order to catch up to the class before the certain target time. Here's how it works. The student can set a target time by clicking on a flag and putting it in the desired location on the progress bar. Once they start watching in the recorded mode, with a 1.5 playback speed, they will see that they will be late to their target time with a speed. So they increase the speed to 1.7, and now they know that they will be able to catch up in time. Based on the metacognitive consequences that we learned about in our formative study, we design our metacognitive design elements to enable cognitive offloading, and we do that in 3 different ways. The first one is topic-based cognitive offloading. Topic is a very important factor in multitasking, and when students are distracted, they might miss changes in topics. We choose lecture slides as a representation of the topics that are being discussed in the lecture. The student has access to the upcoming lecture slides in the form of thumbnails under the progress bar. They can hover over them, they can see the content, and if they want to get notified when a certain topic comes up, they can click on the thumbnail and bookmark it. Time-based cognitive offloading helps them with time management and to control how long they stay away from the class. They can simply click on the timer button once to set a 1-minute timer, twice to set a 2-minute timer, and so on. Activity-based cognitive offloading helps them be notified when there's an event happening in the lecture that requires their attention when they're away multitasking or they're watching in the recorded mode. When a question is asked in the lecture, they will get a notification and the question will appear on the screen. Our evaluation of our cognitive design elements in Time Turner happened in a within subject user study with 20 participants. And we compared Time Turner to a baseline that simulated a normal online classroom. Our experiment had 3 main components: a primary task, a secondary task that together made up the multitasking, and a learning evaluation that followed afterwards and measured their learning outcomes. Our primary task was a memorization-based learning task. We used recordings of an actual introductory biology course to have ecological validity. Each lecture was 10 minutes long, and we analyzed the content for density and difficulty to make sure that they are similar across both conditions. On top of that, we made sure that the order of the conditions and the lecture contents were fully counterbalanced. At a certain point during the lecture, the students were asked to move on and start working on an assignment or the secondary task. The secondary task needs to be a high cognitive load task because we wanted to ensure that the cognitive consequences actually occur during our experiment. We designed a reading comprehension assignment that took 2.5 minutes of the 10 minutes of the lecture, and the student had that time to work on the assignment at the same time as listening to the lecture. After watching the lecture and multitasking during it, we wanted to evaluate their learning, and we asked them to take a quiz that contained 30 true or false statement questions. We chose this format to ensure full content coverage, and the students had the option to choose another option if they already knew the answer to that question before watching the lecture. We wanted to remove those questions from the analysis to account for their prior knowledge. To dissuade students from randomly guessing, we penalized wrong answers and asked students to leave them blank if they don't know the answer. We compared students' grade across both conditions in 3 different domains. The first one was a total grade. The second one was the multitasking grade. The multitasking grade was the students' grade for the duration of the lecture that they were busy multitasking and working on the assignment as well. And lastly, we had the non-multitasking grade for the sections that the students were not multitasking. We saw a statistically significant improvement in students' grades in their total grades and their multitasking grades. There was a 7.5% improvement in the mean grade for the total grade and a near moderate effect size. For the multitasking grade, there was a 13.3% improvement in the mean grade and an above moderate effect size. We also studied the difference in the non-multitasking grade because we were interested to see if watching with a faster playback speed will affect students' non-multitasking grade when using time turner. But there was no significant change across the conditions. We had positive qualitative feedback from our participants, and 95% of them agreed that they would use time turner if it was accessible in their online classes. 95% of them also agreed that they find time turner helpful for their learning. We evaluated our metacognitive design elements qualitatively with 9 participants. We asked them to go over scenarios and tell us how effective they find these design elements for their learning. In general, the outcomes were quite promising, but compared to time turner, our participants found time turner more effective for their learning. Our approach in this work and in designing time turner was to facilitate in-class multitasking and not eliminate it or reduce it. And that's in contrast with this traditional belief that in-class multitasking should always be prevented. We should recognize that university students are adults that pursue many different goals in their lives. And it's important that when we're designing to improve their learning experience, we respect their autonomy and support it by letting them choose what they think is best for them. Our design elements in time turner are not only effective and helpful for in-class multitasking, but they can help students learn at their own pace. Providing this Bichronous learning environment that allows students to go back and watch a section of the lecture that they didn't understand the first time while being in the live class helps provide self-paced learning in a synchronous setting. For students with conditions similar to ADHD, this design helps them compensate for their attention deficit and, as a result, improve education accessibility. Finally, it's not only for online learning. There are other situations where multitasking is very common in synchronous settings. For example, in online workplace meetings, multitasking is also very common, and the same solutions can apply. And with how prevalent it is for university students to use laptops in their in-person classes, and how common it is to have the content recorded and live streamed, using the same solutions to have better positive multitasking and self-paced learning in in-person classes can also be possible. We demonstrated the effectiveness of our design in improving memorization-based learning, but a longer-term longitudinal study in real classroom conditions and focusing on other types of learning and not only memorization, and having more participants can expand on the findings of our work. Our qualitative evaluation of the metacognitive design elements was only a preliminary step, and it motivates more research on these design elements. Finally, we took on a student-centric approach, but analyzing and studying instructors' and teachers' perspectives on in-class multitasking can be a very beneficial addition to the findings. Our contributions in this paper were design elements that support positive in-class multitasking by reducing its consequences for memorization-based learning. Our formative study provided us with new empirical insights onto students' perspectives about in-class multitasking and provided us with structure and scope for our design process. Thank you very much for listening.